hey, if you're interested in the real life performance of one of these currently quite popular 12-volt air conditioning units of eBay, you're in the right spot, because I plan to run such a test on the bench and determine how many BTUs or watts one of these units provide. Because I got confused by all the information these sellers provide that is quite conflicting. Like they're talking about 12,000 BTU cooling performance, and then one line below that they say it's cooling performance is 2,000 watts, and these two numbers don't add up. And the other thing that really bothered me was the fact that nobody is really providing any information how much refrigerant goes into one of these devices. So therefore, I said to myself, let's test it. So let's start with a typical example of eBay here, a universal 12-volt underdash air conditioning compressor kit for 394 bucks. Comes completely with hoses and harnesses and all these things, and that's actually the unit I tested later in the video, and the hardware is quite convincing. Also the compressor is a really good quality, nothing to complain here. The thing that kind of throws me off is the performance specs that they put out here. So they're saying this unit has 12,000 BTUs, and most of these 12-volt air conditioners, they claim to have about between 10 to 12,000 BTU. And they also, just the line below, say it has between 1,800 and 2,000 watts. So BTUs, British thermal units, can be directly converted into watts. And if we do that, all we have to do is multiply the BTUs by 0.293071, and that would be 3,516.8 watts. So almost double of what they claim down here. And if we convert 2,000 watts to BTU, all we have to do is multiply by 3.41214, and we get 6,824.2, so almost half of what they claim up here, which, yeah, makes no sense. And that's exactly why I wanted to find out what the actual performance is. So I can tell you already what I found out is that we are much closer, of course, to what they claim here, which also makes sense when we compare the actual power consumption. So this 792 watts is basically roughly what the unit pulls, about 60 amps on the full load. So not the 50 they're claiming up here. So really the specs are all over the place. But this number here is close to what it really consumes, and this here is close to the real cooling output, what I could measure. So yeah, again, most of the units you will find on eBay run about these numbers, and most of them use the same compressors, and it's kind of a standardized system, so I don't expect any big differences in there. I mean, if you have a different opinion, let me know. But so just as a quick benchmark, in order to provide 12,000 BTU, if we go for a Coleman air conditioning unit, this one here has 11,000 BTUs, and it consumes 9.5 amps at 115 volt. So if we run the math, 115 times 9.5, we get 1,092.5 watts. So you can already tell by these numbers that this is much more closer to reality, because yeah, we are pulling like 300 watts more than the air conditioner unit I just showed you, this one here. Also, this one is a 12 volt unit, so at 12 volt you have less efficiency than at 110 volts. The losses are way higher at lower voltages. So before I dive into how I bench tested my air conditioning unit, here some really important information. None of these air conditioning units on eBay come with refrigerant included. At least I didn't see any. So you have to buy the 134A gas separately. And if you type that into eBay, 134A refrigerant, all the results that you will see are EnvioSafe R34A replacement refrigerants. So what these are, they are a mix out of propane butane gas. Actually, they're not authentic 134A. In general, a pretty good solution, a pretty good refrigerant, because it usually offers even better cooling performance than authentic 134A. But in case of this air conditioner, it's not going to work, because I tested it in the second half of the video roughly. I wanted to see if I can get a better performance with this refrigerant versus the original 134A, and the unit did not work at all. So in case you're having issues with one of these cheap 12 volt air conditioners, make sure you're not using this, but you're using authentic 134A that you can usually buy in car part stores and so on. This is how the unit arrived. We have a bunch of hardware here, brackets and O-rings, some dampers for the compressor, a dryer, bunch of hose, the evaporator, and these come with different front pieces. I think all the rest here is the same. So this one here is made to connect air hoses onto it, which is what we need for our project. And yeah, I already took some screws out here, because I want to take the evaporator core out and submerge it into water so we can get our reading. So I will show you the insides later. The wiring harness, the condenser and a fan, and here, last but not least, the compressor. So yeah, for now, just going to hook this up briefly in this little trailer here. It's the perfect test bench, because I can cover it at night and run my tests, and I can just use screws to attach stuff to the wood. I need to add that no manual came with this set, so nothing whatsoever, absolutely nothing. There was just those parts in the box. And right now I have no clue how much refrigerant we actually need to get this running sufficiently. So for that reason I'm gonna start with 134A, and hopefully we get some good pressure readings that I can compare to other sources online before switching to the hydrocarbon refrigerant and measure that performance. Okay, I got all the fittings tightened, no problem. The whole setup took me about 40 minutes from the beginning to now, which is quite satisfying. And now it's time to evacuate the system. And yeah, since I don't have a clue how much refrigerant has to go in here, we have to connect both the high and low side and read the pressures once the thing is operating. Normally, just filling it on the low side should be enough. Yep, it's so difficult to work with one hand. So close. These things are so counterintuitive. They're closed the opposite way you would close a water tap. Right, the quick connector for the high side. And that's another thing, the high side is... Oh yeah, no, it's right. Low side is blue, high side is red. That's correct. Okay. Got that. Now we're gonna hook up the hoses and all that, and the the vacuum pump. These hoses have little plastic inserts in here, and they like to fall out, so always make sure to check if they're in here before connecting them. Ask me how I learned that lesson. So, quite important. Alright, got the gauges hooked up. Can fire it up now. So it's already reading 0 because it's just evacuating the hose here. And oh yeah, now we're draining the system. Okay, this has been running 20 minutes or so. Gonna shut these off now. Oh, this one was closed, but okay. Doesn't really matter. No, we let it sit for an hour or so to see if there's any drop. Okay, vacuum has been holding for like 2 hours now. We're all good to go. I'm going to fill this up with 600 grams of refrigerant. It's my best guess. It's what most of these systems take as an initial charge. And then we're going to read the pressures once that thing is running. Okay, got this on the ground now. We're reading 2 grams. And I start filling now. Flowing. Okay, that took 40 grams. Now we're gonna fire up the compressor. So now I turned this on. The compressor starts. Pretty cool. Okay, we're sucking in more coolant and more refrigerant. As I said, I'm gonna go to 540 because the scale reset itself before, and we see where we are. We're at 90, 100. Okay, got the evaporator fan hooked up. Not cooling yet. We're only at 220 grams. I had to hook up the fan here because the condenser got way too hot. So we are at 300 and something. 330 grams. Much better. Okay. Okay, we're at 600 grams now. And pressure readings are like this. I gotta check now what the aim is here. But it seems to cool nicely. I need to hook up temperature sensors and all that to get a better idea. But it's ice cold, that's all I can tell. Oh yeah, very nice. So the dryer, I think, indicates still a bit of low refrigerant. Too many bubbles in there. It should have only few bubbles going through here. It's either a sign of the condenser not being cold enough or still low on refrigerant. And the whole setup is currently pulling 47 amps, 50 amps, so that includes both fans and the compressor. So that's not a peak performance yet, but we'll see. Okay, I had to add about 1 kg of refrigerant to get the proper pressure readings, like 130, 150 psi on the high side, and yeah, it's cooling very well. So I'm gonna use this as a baseline now and start measuring superheat on the evaporator and the condenser and go from there. Good morning, it's the next day, and I did some trials yesterday, and I learned that actually the green cable that is connected to the HX port here in the back, that should be the signal line, was providing a steady 12 volts to the compressor, and that would let this thing run at a full speed all the time. So what I did now is I used the line that goes into the fan motor after the resistor, which is controlled by this switch here, and I use this as a signal line going into the compressor. And now the system really changes speed when also changing the settings on this knob. As far as I can tell, the system really cools beautifully running on the low setting. Actually, I want to kind of test exactly what we get out of that setting. So I'm gonna start by now launching it again. Today is much warmer than yesterday. Read the pressures that we get and take it from there. Okay, let's fire this thing up on number 1. So sharing the pressure readings with you here. Low side pressure is too high. High side pressure would be okay, but yeah. So yeah, these numbers have been perfect yesterday when it was much cooler outside. Now we're getting readings on the higher side, which would indicate that we are overfilled. The low side should be below, like around 30 or 20. And this one, yeah, it's okay. So the thing is, they are not providing any manual, as I mentioned, with the unit. So we really have to kind of do our own due diligence to get this right. And anyway, I'm gonna let the system stabilize for a bit and then dive into measuring this properly. Yeah, the low side pressure is dropping still. Yeah, let's see. So I think I found a relatively good spot at a 140 psi high side. Again, it's still 75 degree outside, and with that I could get the temperature at the evaporator to 48.5, so that's around, the superheat is around 17 there. Still not perfect, but so far that's the closest I could get. Again, our condenser line, basically the temperature remained unchanged in the whole test, no matter what the high side pressures were. So it's really not a reliable way to measure subcooling here, to my opinion. I mean, I'm really no specialist on ACs, but this number is not changing. So the only place where we saw changes is evaporator outlet, and the amperage is also the lowest right now. So yeah, so at that point I really want to measure the BTUs, and for that I already opened the housing here. Let's see. So we got the evaporator in here. Ooh, damaged. Well, that's not a big deal. I can straighten that a bit. Let's take this thing out. Oh, that's nice and light. These are heating coils that can be connected to the coolant system of the car to use it as a heater. Also, we're not gonna need that. And yeah, next is I'm gonna dive it into this bucket here. We have exactly 50 pounds of water in this, 6 gallons. And we're gonna measure how long it takes to cool these down by 10 degrees. And with that we can calculate the BTUs. I'm gonna show you the formula in a minute. All right, our 6 gallons of water. The evaporator ready to take a bath. And I try not to submerge this piece here, because that's reading the evaporator outlet. Oh yeah, that works good. See if we can twist this hose here some way. I think I'm just gonna clamp this down. I like it. Perfect. That looks good. Okay. Now, that's our sensor for the evaporator temperature before, and we're just gonna use it to measure the temperature of the water bath. So I make sure that stays always in the same place at the bottom, because cold water goes down or close to the bottom. Maybe clamp it to here. In addition, I'm gonna use a spoon or something and stir the water. But so far, very crude, but that should give us some results. All right, fire on the hole. I'm gonna go full speed. Let's see what happens. So I've been running this 15 minutes now, and I just noticed that the valve, the thermal expansion valve, is freezing up. I think it's because I started with a too low water temperature. The water was only 70 degrees or something like that. So I can also tell that the pressures are really low now, and the amps. So I guess I stop testing at this point, just crunch the data and see where we are. Yeah, we are drawing only 42 amps, so I think this water has to be at least 100 degrees to get a meaningful result, kind of reflecting the hot summer day. And then I try that again. So we can see here how I ran the test. Let me try to get this a bit larger. I started the test right here at 5:05. This is when I dropped the probe into the bucket, and the water temperature was 72 degrees. So it's saying 71.7, that's okay. And you can see how quickly this drops down. Amazing. Every time I was stirring the pot, let me see if this is more clear here. So every time I was mixing the water, the temperature went up. So every time I was mixing the water, the temperature went up, because yeah, it settles at the bottom, it's clear. So we effectively, that was exactly 20 minutes, so we cooled 6 gallons of water from 72 degree to down to the temperature it has now, which is 45. So that's the metric we're going to use, 20 minutes, and the temperature dropped from 72 to 45 degree. And we're going to calculate with that. All right, in order to get to our BTU removed numbers, all we have to do is convert pounds of water, in our case 50 pounds, by the temperature delta. So temperature delta is the starting temperature minus the end temperature, 72 minus 45. That's 27. So 50 pounds times 27, we end up at 1,351 BTU. And then we go and convert our 1,351 BTU to BTU hours, and all we have to do is basically divide this by 0.33, because it was running 20 minutes. So it's 0.33 hours. And with that, we end up at 4,057 BTUs per hour. That, of course, is way too low. That unit is advertised as 10,000 BTU. But first of all, I'm still not sure the charge is correct. And we had the evaporator freezing up. And we can clearly see this here at the, we can clearly see that here. The red line is the evaporator outlet, and it was at 42.8, the lowest it has ever been. Okay, it's the next day, and I've heated up this bath here to about 90 degrees. Just with a little heater here. And now I'm gonna kick in the system. I hope this time we're not gonna have icing here on the expansion valve. So I'm gonna mix this bath up one more time and then kick on the system. And I'm gonna give it some time. I'm gonna give it some time to first to settle the temperature to 85, and after that start counting until we reach 60 degrees in the water bath. And we are pulling about 50 amps at the compressor. Yeah, let's see. So sure enough, I have the temperature sensor, my temperature logger acting up right in the area where it was most important to track the data. So here in this period from 11:57 to 12:02, 5 minutes, it was only reporting temperature 2 times 5 minutes here. So this is roughly where we reached 60 degrees. I'm gonna use this as a benchmark, but I have to repeat this test. So it was right at 12 o'clock and we started the test. Here we were at 85. So at 11:52, that's 10 minutes to drop the temperature from 85 to 60. Well, that's much more promising. Let's see what that is in BTU. So in this test, we used a round number. We cooled it down from 85 to 60, which is 25 degrees. That's 1250 BTU. And we did that in 12 minutes. So that's 0.2 hours. So 1250 divided by 0.2 is 6250 BTU hours. Yeah. The pressures were 160 to 30. Compressor outlet was 152, and condenser in 71, so we lost all the heat just in the hose. Condenser out 70. That's really amazing how much this hose cools already. So I've been switching on the heater. Again, in the bath we are at almost 90 degrees. I have to stir it up one more time. It's 88 right here. And then I will run the test again. Starting at 85, and then we'll measure again down to 60. And I also have some interesting data here. I realized that in 20 minutes the temperature in the water bath increases by about 64.5, 62.5, how you can say, okay, 2 degrees in 20 minutes. So every 10 minutes, 1 degree. And I'm gonna deduct that from the next test. So we kind of factor this loss in through, it's just a plastic bucket open in the space. So it should be isolated for a proper test. But I think doing that, we can kind of compensate for that mathematically. All right, let's go to the pot. So we're at the water bath. Temperature is 88.6 right now. We're gonna stir it up and see what we get, because hot water goes to the top. I think we're gonna be over 90 now. Okay, let's see. Every time I stir it up, 89.8. Yeah, so I'm gonna start the equipment. 90.3, perfect. Let's unplug it and crank the thingy up. That's that. Full power. Yeah, almost 60 amps now. The needle is going crazy. I have to throttle this a bit. Oh wow, almost 200. Okay, interesting. Temperatures. $130. Yeah, it's still heating up. That's gonna take a while. It dropped to 90 to 80 in like 1 minute. It's amazing, but yeah, cold water goes to the bottom. I have to mix it up. Let's see. It's amazing. $82. Wow. It's really hard to get a good reading here at measuring at the bottom. Maybe I put the probe a bit higher. Yeah, that's much better. Now we had 85 at least. Yeah, gonna leave it there. So we are at 60 now after 10 minutes. That's pretty good. I'm still stirring to get a more stable data. 59. Yeah, looks pretty good. So let's look at the data. Data doesn't lie. This is when we started the test, and we can see how the temperature, this is when the probe was at the bottom. It dropped tremendously in just 121. It dropped at 121 to, in 1 minute, it dropped like by 10 degrees. Amazing. And then I raised the temperature probe to be more in the middle of the bucket, which is right here. So to get it to 85. Yeah, right here. So that's going to be our starting point. 123, 32. 123, 23, 32. And then, because I mixed the bucket at the same time, here was another period where I stopped mixing. You can always see, but it doesn't change the complete thermal event. And then we reached 60 degree at 134.15. 134.15. Okay. Yeah, so the first water test we were at 11:50 minutes and now 11:15. So a bit faster, but wait a minute, when the bucket is below 70 degrees. Yeah, I think this cancels. The bucket lost 1 degree in 10 minutes. So over 70 degree, outside temperature 70 degree, we lose heat to the environment, and then below 70 it reverses. So I think it cancels itself out. I'm just gonna neglect that loss in this calculation. So we are a bit better than before, but I think, yeah, we can conclude that it's basically the same result as before. Super cool. Okay, one more test, this time with a bit of higher refrigerant pressure. We are at 87 degrees, and I'm going to inject some more refrigerant. Just a tiny bit more, so we are at around 200. And I want to see if I get an improvement in the performance. Oh yeah, wow, that little bit we are at 60 amps, so it's pulling way more current. Maybe a tick more. Yeah, I want to try around 200 instead of 160 psi, and then see what BTU rating we get. Okay, quite interesting. That was run number 3 with the higher pressures, and we ran most of the time at 200 psi high side, 40 low side at 58 amps. And the temperatures, well, they're not so crazy different, but one remarkable thing is the condenser outlet got warmer this time, and we were pulling 6 amps more. So that's significant because the other 2 tests were 52. But now to the interesting part. Let's see where we are here. So we started, where did we have the first? Here at this time, 1452, and 13 seconds was 85, and then we reached 60 at 15:01:55. 15:01:55. 15:01:55. So 15:02 basically. So yeah, 14:52 to 15:02 is about 10 minutes. Before was 1 minute and 15 longer. Let's convert these numbers and see what we get. Alright, so at these pressures, same formula, we stick to the 25 degree, and this is 10 minutes. We are reaching 7,500 BTU per hour, which is a quite significant increase. So at this point, I'm wondering if I should do another round with a little bit even higher pressure and see what this brings up. I decided before I run the next pressure level, I decided to get pressures with the fan assembled, just to make sure I later know how to translate this data. So I noticed the pressure readings are totally different once the evaporator is in the bath. And I just want to compare, be able to compare it later. So the system has stabilized now. We're at 150 high side and 20 low side. We are pulling 57 amps. Outlet is at 130 and 70 going into the condenser. So now I'm gonna introduce some more refrigerant to get the pressure up. Almost at 60 already, 60 amps and 170 now. Again, we're not in the water, right? So I'm assuming once the water bath is at temperature, we are way over 200 here. So I don't want to do too much, just a tick more maybe. Pulling 61 amps. Yeah, we'll see. Now we're getting close to 200. Okay, we are 200 now. 25 on the low side. And this comes up once the evaporator dives into the bath. Pulling 63 amps. I think I leave it there. And prep the water bath to 85 and then we submerge our evaporator again. Last test with 134A before we switch to carbohydrate refrigerant. The water is at 80 something degree. Fire the thing up and get the readings. So we've been running for until we reached below 60, so the pressure was most of the time around 220, 230. Low side at 35 again. And we were drawing 62 amps before the temperature dropped below 62. Compressor outlet 174, in condenser inlet 68 and outside temperature 77. Yeah, gonna take notes and run the numbers. So this time with the higher pressures, it ran exactly 10 minutes again, like before. So that's a pretty clear idea. So we had 85 here at 1622. And we reached 60 degree at right here, 1633. So roughly, well, pretty exactly 10 minutes, but we consumed more electricity, 62 amps versus 58. Up here was 58 amps. So 200 is clearly the sweet spot. So 160 if the condenser is not submerged. That's where I'm gonna dial in those systems now. So now we can finally run hydrocarbon refrigerant. Yeah. So it's the next morning. We are recovering the refrigerant, the 134A. I'm pulling a vacuum now. And I did that with this old fridge compressor here, 12 volt, runs great. Through a condenser made from copper coil back into the tank. And next we're gonna fill the system with this hydrocarbon propane butane mix. They say this should provide a 5% performance improvement while drawing less power. Well, we'll see. We're gonna have the data to prove if this is a myth or true. So let's see. So we're filling the system. The can is freezing up on the low side here. I think I have to swap to the next bottle. And I noticed they have a dye in here, which is not so cool, but yeah, we'll see. Okay, I switch over to the next bottle now. All right, got the water heated up to 90 degrees. Our hydrocarbon test number 1, ready to go. Oh. Okay. Let's see. At 50, we are at 58 amps, so it looks like it's the same current draw as yesterday. Outside temperature is a bit higher. We had 75. Compressor output at 140. Temperatures look pretty much the same. And the low side pressure is higher. Oh no. Huh, that's interesting. Well, we were at 200 yesterday with the water at this temperature. So anyway, yeah, I have to gather some more data. Make sure this is mixed up while I'm running the test. Let's see what the numbers tell us. I just noticed the amperage went down all the way to 50. After just a few minutes. So we are 12 minutes in and the water temperature did not even reach 70 degrees yet. That's a total bust. We've been running at about 40 amps. And yeah, the performance I can tell already is by far not the same. I have to calculate the BTUs, but we're way below. So while I'm at this test, I think I'm gonna add some more gas and see where we get, because the low side pressure is way too low. So this stuff here was a total flop. What happened was the valve froze up, the expansion valve plus the pipe, the tubes behind here. I'm gonna blend in some pictures that I took before. The temperature of the compressor went over 200, at the outlet 250. And we had a really strange pressure reading here. Well, I guess it was close to 0 on the low side and 200 on the high side. And I think it's because the expansion valve clogged up internally. This is how the evaporator looked like. Thick ice here, which is not normal. It did not happen with 134A. That would explain the strange pressure readings. And well, obviously the performance was also quite bad. Yeah, we reached 3,214 BTU per hour, which is bad. And yeah, I don't know, there's not much to add to that. Okay, so I did some more research to figure out why our evaporator would freeze up running this 134A replacement refrigerant. So as far as I can tell, the reason is the metering valve that comes with this particular 12-volt air conditioning set is a thermal or thermostatic expansion valve, which measures the temperature at the evaporator outlet and opens and closes accordingly. And these valves need to be specifically designed for whatever refrigerant is running in the system, so it's not interchangeable. And therefore, yeah, we were seeing those crazy pressure readings completely out of whack, and the evaporator building ice up. So as far as I can tell, all these 12-volt units come with this TXV valve. I have not seen one with a orifice tube system which could work with this refrigerant, but yeah, correct me if I'm wrong. As far as I can tell, all of them have the TXV valve. So in case you bought a 12-volt air conditioner of eBay or Amazon, and you also bought the gas online, and you're not satisfied with the performance of your unit, look into this, because as you can see in the test results, I only reached 4,000 BTU with this combination versus 7,500 with the authentic 134A gas. So running the authentic 134A on an 80-degree day with about 80% humidity, we would see 150 to 160 psi on the high side, 20 to 25 psi on the low side, and the compressor was pulling 57 to 60 amps. And whenever during my test I lowered or raised the refrigerant level, the current draw of the compressor would change accordingly. So it would go down to almost 40 amps when it was really low, or up to 80, 90 amps when it was too high. To my opinion, or based on my data, the current draw of the compressor is the best indicator if a system is properly filled. That's just my conclusion. By no way, I'm not an air conditioning specialist. It's just based on my data. So you might want to double check that on a 80-degree day. Put your air conditioning system on full blast and see how many amps the system is pulling. The efficiency of that air conditioning system is quite good, actually. There's a metric called EER. I don't know what it stands for, but it's a metric you find on all air conditioning units you can buy in a store. And a good air conditioner is between 9 to 12 EER, and this unit reaches 10.42. So all we have to do is divide the BTU by the power consumption in watts. So we had a, let's say, 60 amp pull multiplied by 12 volt is 720. If we divide 7,500 BTU by 720, we get ER of 10.42. And I consider this as pretty awesome for this little unit, right? No complaints here. Now, when it comes to using such an air conditioner in a vehicle, I think we have to be kind of careful, because A typical automotive air conditioner, as far as I know, has up to 14,000 BTU. And we have like half of that with this unit. So we cannot really expect this air conditioner to deliver identical performance of a regular automotive air conditioner if it's only consuming half the energy to do that identical job, basically. So we bought this device to be mounted in a small European RV, and that RV is 25 years old. It came originally without a factory air conditioner, and we wanted something that help cool the vehicle down while traveling and also when parked at night. So this air conditioner has no problem cooling the cabin of this little camper down. It works great, absolutely perfect. So that would be my conclusion on if it was worth it or not to buy this unit. Depending on where it's being applied, it definitely does an awesome job. I will post a follow-up video about the conversion we did in that camper, how we installed it. We were able to spread everything out due to this unit being an underdash unit, which is quite nice because we could mount the compressor far away from the living area. And we also added a huge 628 amp hour lithium iron phosphate battery to be able to run the air conditioner through a whole night. So at full blast, it should run 10 hours with this battery. 60 amps times 10 is 600, so we still would have 28 amp hours left. And in order to charge that battery and also run the air conditioner while traveling, while driving, we added a second alternator, a water-cooled alternator, because the standard alternator that came with that RV only delivers 80 amps and it's air-cooled. So if we would try to charge this gigantic lithium iron phosphate battery, a regular air-cooled alternator, while idling, can only deliver current for a short period of time before it starts overheating due to the restricted airflow. So therefore, we decided to mount this Audi alternator with 190 amps to the vehicle. We built a separate pulley system. And yeah, that's all coming up in the follow-up video. And as a bonus, we also added a plate heat exchanger in order to extract the waste heat energy of the air conditioning system and heat our shower water with it. That heat exchanger looks like that. And we tested the performance of the system, measuring the BTUs. You know the method already. It works awesome. So we have free shower water now using waste energy. We have an air conditioner that works while the vehicle is in motion, and we can charge a gigantic lithium iron phosphate battery all in one package. So if you're interested in that, please hit like and subscribe, and we see you soon.